So I hope everybody's been having a nice summer. The weather hasn't been too bad where you are. Actually, in New Jersey, it's been very nice the last month. We had a hot July, but August was quite mild. So, did everybody get to do the reading? Did anybody not do the reading?
I've read at least part of it.
Yes.
Okay, good. Well, let's start with a general question. Does anyone want to explain Planck's method in arriving at the concept of quantized energy?
He was shooting beams of light at a metal plate.
No, that's later.
Okay.
All right. From the reading, all right, let's start with the black body. So, does anyone want to explain what black body radiation is and why people were interested in it at the turn of the 20th century?
Black body radiation is when you heat a black body, and it gives all, depending upon how much energy you put into it, you get a certain amount of radiation out of it. As in a light bulb, when you put electricity through
Right,
it and you get
right.
light out.
Is it related to the equipartition principle?
That was part of their problem. Yeah.
Yeah.
So
So
do you want to describe? That's a correct description of what black body radiation is, right? So they actually took a black painted cavity,
Yeah.
and they heated it, and then they put a little hole so they could take the radiation out. But basically, the radiation was, in their view, in equilibrium with the heated sides. So that was the black body.
Yeah.
So that's a correct explanation. So what was the problem that at the end of the 19th century, they saw when they actually measured the spectrum?
The problem was that quanta of light are point entities. They don't have a body as gases, and the interest in black body radiation was that they could insert a black body matter into the genes box to affect the transfer between different quanta of light for the equipartition theorem to apply to light also.
Okay, but remember, before Planck, nobody thought, well, let me modify that sentence. If we look back into the history of the study of light, there's an evolution, which looks a little circular, but really isn't. We go back to Newton. Newton did actually hypothesize that because light traveled in rays, that possibly light consisted of particles. Obviously, this is back in the 1600s. But in the subsequent centuries, all the phenomena that were discovered about light could be explained by viewing light as waves. And this culminated, people should remember from our earlier study groups, in Maxwell's theory of light, in which he identified light and other sorts of other sorts of radiation as electromagnetic waves traveling through space. So that was basically where things stood after Maxwell. So Maxwell's discovery, based on the idea that the equations of electromagnetism could actually predict correctly the speed of light. Now, he knew what the speed of light was. There had been early measurements. So he was taking a known coincidence between the ratio of electric and magnetic units, which comes out in the form of the speed of a velocity, and the known speed of light. He put those things together and said, light is electromagnetic radiation. And that turned out to be a really excellent description of the known properties of light at that time.
Yes.
But then what happened, right? What was the basic mathematical structure that led people to conclude that there was a problem with our understanding of black body radiation?
The ultraviolet catastrophe.
Right. So what was the ultraviolet?
It's considering light just as an electromagnetic wave and joining that with the what is it called? Equivalent, I don't remember the name. The theory.
Equipartition.
The equipartition theorem leads to frequency runaway. So there was a need to say that light is and Planck avoids that by quantizing, by saying, well, there is a quanta, and I think he uses black body radiation and to in some part as an element to arrive to that conclusion, but I'm not sure.
Does anyone want to describe what the equipartition hypothesis is?
I'll try. So the idea, I mean, I think it started with like gases in a container, and it said that the total energy in the container would be on average equally divided between all the particles in the container.
Right. So that's completely correct. So yeah, and as Gamow states, total energy is shared equally by all the particles, mutually colliding. Now, as we go forward, we'll actually find out that that's not always true when you take into account quantum mechanics. But this came out of statistical mechanics, thermodynamics, what we were discussing in the last two sessions. So they were trying to apply that to an oscillator or a set of oscillators based on a continuous medium. And the mathematical problem they ran into is that as you consider higher and higher frequencies, there are more and more modes to share those frequencies. And therefore, the amount of energy goes up without limit as you increase the frequency, which of course makes no sense. So that was the ultraviolet catastrophe. They actually understood that even in isolation from the known spectrum. Now, obviously, since that's an impossible spectrum, it also contradicted what they observed. So what they observed was the spectrum that rose to a peak as the frequency increased and then declined sharply. that in essence was the problem. So what did Planck basically do with that problem?
He reinterpreted Wien's displacement law. I don't know how I don't remember how he reinterpreted it. I know that it has to do with the wavelength of emission of a black body when the black body is inversely proportional to the temperature. But I don't remember exactly how, or I didn't understand very well how he reinterpreted that to match his quantized hypothesis of light.
Anyone else?
So, well, what I got out of the reading is that the energy contained in each quantum is proportional to the frequency, which means that at higher frequencies, there's a limit on how many quanta there can be. And so it's kind of the higher frequencies sort of self-limit themselves in that way.
Right, exactly. Now, in that paper, he does not, and this is okay, you don't have to, in a paper, reveal how you came to the conclusions. You can put them in a more educational way. Historically, we know from what Planck wrote in other circumstances that he actually came upon the mathematical formula for the spectrum before the quanta, the hypothesis of energy being quantized. So basically, people had this spectrum that, went up and then it went down. And he pretty much guessed, well, this looks like an exponential fall off on the, everybody knew that the low frequency end was a simple power law. The high frequency end, he basically guessed this looks like an exponential fall off. So he basically guessed what the formula was. So the formula, the real formula, as people see, it's not that complicated. It has the V cubed, the nu cubed, frequency cubed term on top. And on bottom, it has the 1 minus the exponential. So that means that at low frequency, that 1 minus the exponential is essentially unity. The exponential is very small. But at high frequency, that exponential takes over from that term is dominated by the exponential, and that drops the amplitude rapidly. So then he asked himself, what phenomena, what change in our hypotheses can we make to end up with what he now knew was the correct formula that exactly fitted the observations? And that was clearly his brilliant insight, was to jump from that formula to the recognition that, as Annette says, you could get rid of the ultraviolet catastrophe if light was quantized and the quanta, the energy of the quantum was directly proportional to the frequency. So then he took that insight and did what he does in the paper. He derives the formula from that change in statistics. And of course, the ratio between the energy of a quantum and the frequency of light is now called what? What is that ratio?
Planck's constant.
Right. Now it's interesting that the dimensions of Planck's constant can be interpreted in a number of ways. The dimensions are mass times velocity times distance. Now you can interpret that either as a quantity called action, which is the product of energy and time, or, and this will emerge pretty swiftly as we go on in quantum mechanics, you can interpret it as angular momentum. So, as was discovered as they went on in quantum mechanics, the fundamental unit of angular momentum is Planck's constant. That's the smallest angular momentum any object can have. Strictly speaking, it's Planck's constant is divided by 2. So, all right, so that's how we got to that point. Now, going forward, then basically what happened. So Planck publishes this paper, which has joined us. Oh, Charles, hi. So Planck publishes this paper at the very start of the 20th century. And as I showed you in that little chart that I sent, the very last years of the 19th century, the very first years of the 20th century, basically mark the beginning of this fundamental revolution in physics that extends well into the first half of the 20th century. So basically, he hypothesized that energy was quantized, or at least that as a minimum, that matter had to absorb and emit energy in these quantums, in these distinct quanta. So what happened next?
Einstein took the idea of the quantum and then kind of ran with it in his work with relativity. Didn't he establish quanta as like it's not just what's absorbed or emitted by matter, it is like a freestanding, free-floating entity on its own.
Well, basically, right. In other words, well, you were about to describe what
the photoelectric
his
effect.
discovery with the photoelectric effect, which is one of the key papers that he wrote in this extremely productive year of 1905. So we're 5 years further on.
Einstein established that there was a minimum amount of energy for the electron to break the surface of the metal, and that energy was dependent on the type of metal that you were taking into account.
Right. But how did that demonstrate that light was traveling as a quantum?
Because it is the collision of one single quanta of light with one electron, and from that collision, the electron might exit the surface of the metal or not. So it follows that quanta has to have enough energy to dislodge the electron and get it out of the metal.
Well, Sam, what is the difference in observations that Einstein used? What is the observational effects that Einstein used to distinguish light quanta from light waves?
higher frequency or higher intensity. That he said that for varying intensity, the energy of the photoelectric electrons remains constant, but there was more photoelectrons. And for varying frequency, what changed was the energy of each photoelectron.
Right. And
Was he
what
trying to
else?
observe like collisions between light quanta and electrons? No, that was Compton at the end.
No, he was observing the electrons coming off. But
Mm.
what, other than that, the frequency of the light was related to the energy of the electrons coming off, what was another extremely important characteristic of the electrons versus the frequency?
Oh, is this on page 25 where it's the energy remains constant of the electrons at different intensities at the same frequency?
That's one thing, but the other thing, I'll just say it, is the threshold effect. That
Oh,
if you,
yeah.
the key giveaway that these were quanta is that no matter how intense the light, for a given material, there was a threshold in frequency in which below that frequency, no electrons would be emitted. And if you think about this as, you know, the way I like to think about it is compare this with what you would expect from ocean waves, water waves on a beach, right? No matter what the wavelength of those ocean waves, each wave is going to pick up some pebbles. Some pebbles are going to get moved. If you have a storm and the amplitude of the waves gets very big, you've got huge amounts of pebbles and you can wash away an entire shoreline. But it doesn't depend on the wavelength of those waves. You always are moving pebbles. But here we have observations that no matter how big the waves are, it could be a tidal wave of light coming in at, let us say, infrared radiation, but nothing above this threshold. None of these little pebbles, and electrons are a lot smaller than pebbles, get moved. So that was, you know, Einstein's really very significant contribution as saying, look, this is clear proof that these must be quantum. And then, of course, when you plot when you go above that threshold, then the energy of the electrons goes up as the difference between the energy of the photons, as the difference between the frequency of the photons and the frequency of that critical threshold. So that demonstrates that, again, we'll get into the caveats on this, that in this respect, the light is traveling as quantum. But remember, by this time, everybody knew that there were many, many phenomena of light that could be described as a wave. Diffraction, refraction, reduction of spectra, all the phenomena that was observed in earlier centuries and was accurately described by Maxwell's theory of electromagnetic radiation everybody knew that those wave functions didn't go away, but you had an addition that the light was clearly quantized. So, okay, so any questions in general on this?
I guess I had a question about that threshold. So there's like it only starts emitting energy at the level of the quanta, right? But I was thinking of that like, I don't know, like quanta has like different steps, right? Like you reach one threshold, but then why isn't there like another threshold that it starts releasing like a higher amount of energy? Because it after you hit that threshold, then the amount of energy really starts going up linearly.
What
right?
happens in our concept, the present day concept of what happens is that there's a minimum energy, which has this horrible name, whoever came up with it, of work function. It is not a function. It does involve work or energy, but it's a quantity. So there is a quantity of energy for any given material that's needed to tear an electron away from the surface. So remember, the electrons are bound into the structure of any material by their electrical attraction to the ions. Now, in a solid structure, that's pretty complicated because the electrons are being attracted not only to the ion that they're closest to, but to other neighboring ions in a solid structure or a liquid structure. So you have to give to that given electron enough energy to tear it away from that electrical potential. So
Once that is reached, then it
right. So what Einstein's insight was that this must describe a process in which a single quanta of light gives energy somehow to a single electron. Again, this is very different than the notion of a wave. A wave is going to give energy equally to quadrillions of electrons. But that's not what's happening. It's a single quantum of light giving energy to a single electron. So if it has more energy, and again, just envision that as a gravitational potential. You've got a ball at the bottom of a cavity, and you strike that ball with your baseball bat, which is the quanta, the light quanta. And if you strike it hard enough, it will exit the cavity and go flying off. The harder you strike it beyond that, the more energy it will have, assuming that you're giving up all of the energy in the bat, which is what the photoelectric effect shows. All the energy, either the photon doesn't give up any energy, or it gives up all of its energy. So again, that describes its existence as a quantum. Either it travels through the material and isn't absorbed, or it's absorbed and gives up its energy to the electron. So if, oh, go ahead.
I was going to say, so I was going to ask if there are ever cases of like quanta getting like subdivided into smaller quanta. Like if you had a big release of energy in the this form, this light quanta, and it hit like a surface where there was electrons ready to receive the energy. If it wasn't, is that the case? Like if it was too big or something, it wouldn't break down into a smaller energy packet that was enough to release the electron. It would just move on until it found.
Basically, yeah, the hypothesis of quantized radiation involves the idea that these quanta, which later are named photons, at this time they're not called photons, but we call them photons, are indivisible.
Okay.
So the photon travels until it's absorbed. Martin, you had.
Yeah, I have a question regarding that energy level. So would that imply that what happens if the photon hits an electron not in the maximal energy orbital, but in a lower energy orbital?
Right. In other words, well, first of all, let's take the case where the photon does not have this critical threshold energy. That doesn't mean it can't be absorbed. It means that it's absorbed and the electron, which is still trapped because it doesn't have the energy to escape, it gives up its energy and shares its energy with the other electrons and the ions. And eventually this is degraded into thermal energy. So the photon can still be absorbed. If it's an infrared photon, it's heating things up. Radio wave, the same thing. But, okay, basically what you're seeing in a material is that the electrons that are easiest to kick off, those are the ones that are going to be expelled.
In the highest orbital. Or no?
Well, as I say, you don't have orbitals in a solid material.
But you have electrons with different levels of energy according.
Right, you have electrons with different levels of energy in a solid structure.
Yeah.
Right, so if it's either a metal or an insulator or a or a semiconductor, some of you may have seen these diagrams in which you have these levels. Some of these levels will be so closely spaced, they're basically continuous, and some of them will be widely spaced. But basically, you've got the top of that distribution. That's the electrons that get expelled. So if, again, this doesn't exclude, even if you have let's suppose you have ultraviolet light impinging on a metal. Some of those ultraviolet quanta will hit electrons that are more tightly bound. And since those electrons don't get enough energy to leave, the same thing happens with them as it happens with all the electrons when they're exposed to the infrared radiation. They get more energetic, and eventually they share their energy with everybody.
So
some of the UV light will be transformed into heat. Some of it will be transformed into the photoelectric effect, into electron current. And let me just say, relative to our work at LPPFusion, we had the problem early in the project of how to get the X-ray energy that will be emitted, which is a third to perhaps as much as 40% of the total fusion energy will be emitted as X-rays. How to efficiently convert that directly to electricity. And the problem is, in a photoelectric device, if you have a very thin layer of metal, thin film of metal, most of the X-rays will pass straight through it.
Mm.
But if you have a very thick layer of metal, most of the photons will give up their energy to electrons, and the electrons will share their energy in trying to escape.
Mm.
They're going to share their energy with other electrons, and they'll never make it out.
Mm.
Their energy will be, the electron will absorb the energy, but the electron's energy will in turn be absorbed in the bulk of the material. So the solution that we made for that, and frankly, I thought it was so obvious, I was astonished that it was patentable, but it really was to make thousands of layers. So each layer will take a small amount of that energy and efficiently turn it into the energy of electrons, but only a small amount of that energy will be converted. So most of the photons will pass on, but in passing through thousands of these layers, about 80% of them will be absorbed. So, and have their energy translated into the electrons. And then we set up these little grids at each layer to absorb the energy of the electron and convert it into energy that will feed a capacitor. So this problem that, or this phenomena that not all of the energy of even the most energetic electrons, by no means all, get converted into electrons, that produces practical problems for any photoelectric device.
Could it be that photons that are below the critical frequency could hit electrons, make them jump an orbit, and then when the electron comes back to the original orbit, it emits light?
Well, that's a process too. That's a process. The name of the process, and we use this process too, it's called scintillation.
Yeah, that.
Right. So, but this is not an instantaneous process. And we were discussing this at the lab just the other day. Scintillation is really a form of fluorescence, but a very fast form. And you've described it correctly. The light, the radiation hits the scintillator. The electron is excited and it drops back down
To its rest orbital.
To a lower level. So this is very convenient because there are materials that basically you can absorb a X-ray, very energetic photon, and most of that energy is going to be dissipated, but the atom will emit a photon of light. And of course, light is much easier to deal with than X-rays.
Yeah.
So we are, first of all, we use scintillation routinely. In our detectors, we have plastic scintillators that will scintillate either when a neutron hits a nucleus. The nucleus then moves, setting off an electric impulse that excites the electrons and then the scintillator emits a photon. So it's a neutron detector, and that also happens when it's hit by X-rays. So we can see both of these pulses. Well, over the decades, people have developed scintillators that are a lot better than these plastic. And in particular, the one that we've just bought is cesium iodide. Cesium iodide is a lot more sensitive. So we're going to use this, and we were just discussing this today. We're for an X-ray pinhole camera. So one of the problems that we do anticipate in this next exciting experiment with boron is that the decaborane will break down and some of the boron will be deposited on the inside of the chamber.
Yeah.
And unfortunately, we suspect that that's going to cover up our windows very quickly. So we probably will not be able to use our optical camera anymore. But we don't want to give it up. So instead, we're going to take the X-rays, which can easily pass through the window, even if it's coated with boron, and we're going to put them through a X-ray pinhole. So people know the idea of a pinhole camera. This is an ancient discovery, or hundreds of years old discovery, in which if you simply create a pinhole, you can get an image without a lens because you're directing the rays through the pinhole. So we're going to use a pinhole, which will be made out of tungsten, to create an image in X-rays. And then we're going to have a disc of cesium iodide, which we've already purchased. That's going to convert that image into light, and our optical train will feed back to our ultra-sensitive ICCD camera. So we'll be able to see the plasmoid that emits all the X-rays, even if the windows are blocked.
Is the scintillation backscatter, or whatever you call it, principle of effect, the one behind the X-ray machine for structures that you patented? For the structural X-ray for bridges and stuff? Does it use the scintillation?
No. To a certain, no, that's a different phenomena. What you're talking about is Compton scattering.
Okay, yeah.
So there, the X-ray photons, without being absorbed by the material, can scatter off the material. So they'll be reflected.
That's
so
backscattering, that's what it's
right.
called? Yeah.
So the photon will still be intact.
The
direction of motion will change. Now, the easiest example of a photon change in direction is reflection. Obviously, if you've got a mirror and you've got an optical photon, it can bounce off that mirror without losing its energy. But with X-rays, X-rays don't get reflected easily. But this backscatter will scatter a small, a small fraction of these photons will be backscattered. And then from the same side as your source, you can have a detector, which generally will use these scintillators to detect the X-rays. And that way you can inspect something like a road that you can't get to the other side of, or a bridge, pipeline, things that it's inconvenient to get to the other side of because they're so large.
Yeah, brilliant. Yeah, thank you. Thank you for that.
So let's just summarize where the scientists were back, because we'll see whether this is coherent, but at the moment I'm going to stick to a chronological sequence. And the next class is not going to go further with quantum mechanics. We're going to go to the contemporaneous developments in nuclear physics, relativity, and then plasma physics. So we're sort of going to cover these same decades from the standpoint of the various subspecialties within physics. But as of this point, 1905, you can see basically where people are at. On the one hand, there's been the introduction of the notion of energy, and specifically electromagnetic energy, as quantum particles. On the other hand, we can see that at this time, there's no real integration of the particle nature and the wave nature. But if you look back, this was not, people weren't staying up late at night, as far as I can see, from the papers worrying about this. And it certainly was not, as in popular, contemporary popular versions of quantum mechanics today, it wasn't seen as something supernatural. And I want to emphasize again that if we look at the development of quantum mechanics, at this stage, it was very clear that the question of what is happening was very much isolated from the question of how it's observed. This is something that's going to only arise in future decades. But I think right now, right now being 1905 or shortly thereafter, is the situation that the physicists found themselves in fairly clear? Does anybody have questions about, what the status was at that time?
Well, it seemed like Gamo's sentiment was kind of like, I knew physics had taken root. I mean, it was like part of this, I guess the narrative was like, we have established that like a new model of physics, which was like this wave mechanics versus the more classical physics.
Well, I don't think that Gamo was saying that that's what had occurred as of 1905. He's saying this is the start of the process. And it certainly is part of the start. As I say, what's happening, and even to the physicists of the day, it wasn't entirely integrated, is you have four simultaneous revolutions, which is the development of quantum mechanics, development of relativity, the discovery of the nucleus and of the energy trapped within the nucleus, and the possibility, which was immediately obvious to people, of the benefits of getting that energy out of the nucleus, using that energy.
Right. So
and
of course,
then
we're on the
fourth revolution, which was actually the one that was least integrated into the mainstream, was the development of plasma physics, the discovery of a fourth state of matter, which actually dominates the bulk of the universe outside of the planets. So, okay, well, look,
I did, can I have one question?
yes, Peter.
Was the orbital model implied as early as 1905? When you have quanta, it would seem there are levels that would be analogous to the solar system. It was later picked up, but was that an active concept at that point?
No, in other words, as I say, what was being established in this period was the reality that in some way, electromagnetic radiation was quantized, that there were these quanta later named photons. And remember, this is a period in which the reality of atoms is still being established within physics. So you have, we'll go into this a bit in the next one because I want to get into nuclear physics, probably as the next one. I'll have to decide. But the background is that chemists had developed an atomic theory of matter to describe their own data during the course of the 19th century. Physicists had not entirely accepted that. And there certainly were physicists like Maxwell who were actively trying to explain atoms, which he thought existed in terms of this very well-developed wave theory of electromagnetism. So you have these two strains developing in which atomic theory, matter is quantized, is being developed through chemistry. And as I hope I've illustrated in the study groups over the past year, physics was developing a continuum notion of material processes being capped by the Maxwellian theory of electromagnetism. So already at the end of the 19th century, people are trying to put these together. But it really wasn't until Bohr that people started to look at the phenomena of the atomic spectrum, which remember had been known since, again, the late 19th century, and trying to put together the atomic spectra, the notion of quantization into a structure of the atom. And part of that was obviously based on the very important discovery of the nucleus, because the 19th century atom, late 19th century atom, there was no known internal structure at all. You couldn't have the Bohr atom until you realized that that the atom looked very different if you looked at charge versus mass. You look at charge, the electrons and the nucleus are equal. If you look at mass, there's no comparison. The nucleus is 2,000 times as massive as the electrons, more with most, 2,000 to 4,000 times. So, as I say, it's premature in this class to get into the Bohr theory, because we're going to sort of go through and level the field, as it were, and get all of the knowledge that physicists had at the period of the first decade of the 20th century. So that's what we'll be doing in the next 3 classes. I hope it will take only 3 classes going into nuclear physics, relativity, and plasma physics. I hope it'll be in a month. I'll have to, we're going to be hot and heavy in the lab, but we'll see. Okay, any final questions, and then we should wind up? Or comments? Okay, good enough. So we'll see you all next time, hopefully after some exciting experimental results.